Hi everyone. So now let us talk about another traversal algorithm. It is called as depth first search. Okay. So let us see how DFS works. So the way we implemented BFS, it was an iterative algorithm. DFS is a recursive algorithm, and let us see how this algorithm works. So let us say we start from node 1, we visit this node, and we pick one of its neighbors. Okay, so one has two neighbors, so we will pick one of its neighbors. Okay, and we will make a recursive call on that. So maybe we start with DFS on node 1. Okay, and it makes a recursive call on one of its neighbors, that is 2. Okay, actually what will happen is one will try to make recursive call on all of its children or all of its neighbors, but it will start one by one. To 0 we will come later on. Okay, so from 2 the same thing will happen. We will mark it as visited, and we will see, okay, what are the neighbors of 2 that are not visited. So we make a recursive call on, let's say, 3. From 3 there can be multiple options. We can go to 5, we can go to 4. So let us say we pick one of its child, that is 4. So we come here. Okay, and from 4 again we have multiple options. We can go to 5, we can go to 6, or we from 5 we can go to 6. So let us do this. So it is going something like this: DFS of 2, then we have DFS of 3. So I'm drawing the call stack side by side: DFS of 4 and then DFS of 5. And from 5 we can, the only node that we can visit is DFS of 6. So once you reach 6, you realize there are no other nodes from where you can go. So what you will do, you will return back. Okay, so from 6 you can't go anywhere, so you come back. This goes off, and let us draw it using a dotted line. From 5 you see that the neighbors are already visited, all its neighbors are visited, so you come back to 4. Okay, so you come back from here to 4. Now at 4 you see what are the neighbors I can cover. So you have covered 5, 3 is already visited, 0 is not visited. So what you can do, you can go to this node 0 and you can mark it as visited, and from 0 you cannot go anywhere. Okay, so DFS of 0 will get into the stack, and from here also we will come back because there is no other option where we can go. So we come back to the node 4, and from 4 we again come back to 3. So this goes off, 3 goes off, we come back to 2. From 2 we come back, finally we terminate at 1. Okay, so this could be one possible out. output that could be generated using a depth first search. So what is our output? The output is 1 2 3 4 5 6 and 0. Okay, yeah, this could be a traversal output. So there could be a different possible output also, depending upon if in the beginning, if from 1 if you're going to 0, then 4, then 5, then 6, then 3 and 2. Okay, those outputs are also possible. It will depend upon in what order we are making our adjacency list. So this is simple depth first search algorithm. One thing to note is both these algorithms will take linear time. Okay, linear in terms of vertices and edges, because we are traversing all the vertices and all the edges at most once. Okay, we are traversing all vertices and edges at most once. So the complexity of BFS and DFS, it will be order of V plus E. So in the next video we will discuss the implementation of DFS. Hi everyone, so now let us talk about how we can implement depth first search algorithm on the graph. So we are using the same graph as BFS, and now we are going to write the code for DFS. So this is the DFS function that I want to complete. I'm getting a starting node, and what I will do, I will first create a visited array, because I need to store, or I need to mark what nodes have been visited in order to avoid visiting them again. So I make a boolean array, and it has v number of elements. And since we are going to make a recursive algorithm, I will create a recursive helper function that will help me to do the DFS. So let us call this as a DFS helper, and let's give it some node, let's say node, and let's also give this a visited array. Now we cannot create this array again and again, so we have to create this array only once, and we have to start DFS helper by giving this starting node, that is the source node and this visited array. Okay, so that is why we need a wrapper function to call this DFS helper function, because we can create this visited array only once. What will happen? Let's say, let me draw the graph. We have 1, 2, 3, 4, 5, and 6. So you start from this node. Okay. So you say, okay, go and visit this node. So we say, okay, let us mark this as visited. So here what I will do, I will say visited of node equals true, and I will make a DFS call on all its unvisited neighbors. Okay, this is what we do. So we can say for int neighbor that is there in adjacency list of this particular node, if you can check if this is not visited, if the neighbor is not visited, okay, then you can make a recursive call on it. You can say dfs helper go and visit that particular neighbor. So now you can see this is a recursive call. So what will happen, let us say 1 makes a call on 0, and 0 does the same thing, it makes a call on 4. 4 does the same thing, it makes a call on, let's say, 3. 3 makes a call on, let's say, 5. 5 makes a call on 6, and it comes back. Now 3 sees, okay, I'm making call on all unvisited neighbors. So 4 is a neighbor of 3, it is visited, but 2 is not visited. So 3 will make a call on 2, and 2 will see 1 is a neighbor of 2, but it is visited, it will also come back. So we come back from here, we come back from here, and we come back from here. So after this call, okay, so after this call to 0 has been complete, this for loop of 1 will not run because it will not find a neighbor that is not visited. Okay, so 1 will look at 2. So what are the neighbors of 1? They are 0 and 2. Okay, so once you make a call on 0, 2 automatically gets visited. So this loop will not run for 2. Okay, so this loop will go to 2, but this if condition will not be true. So we will not make a DFS call on 2 again. So that is exactly what we do in DFS, and from here we can simply return. So that's it, that's the code of DFS. And now we can run our code, and we can say, okay, go and do DFS starting from node 1. Let us see the output of DFS. Okay, we have to print the node also, so we can say cout node in order to see what nodes have been visited. You can see it goes from 1 0 4 5 3 2 6. So let us try to visualize what is happening. 1 2 3 5 6 4. This is our graph. So it is going from 1 to 0. Okay, from here to here, then to 4, then to 5, then to 3. Okay, and from 3 to 2, which is fine. From here we come back, and from here we come back here, and 5 now makes a call on 6, and from here we come back, and this is how the output is being generated. Okay, so as I said, the outputs can be different depending upon in what order you have inserted data in your adjacency list. This is called as depth first search. Why? Because we are going deep inside a branch instead of going level wise. Okay, we are not traversing level by level, we are first going deep inside a branch. Once that branch is terminated, we enter some other branch. Okay, so that is why it is called as DFS. So that's all for this video. Thank you. Hi everyone, in this lecture we will talk about directed acyclic graphs, and we'll talk about another algorithm that is known as topological sorting. and this algorithm specifically works for directed acyclic graphs, which is also known as DAG in short. So what is a directed acyclic graph? So let me give you one example of DAG. So directed means the graph will have directed edges. Let's say I have a node 1, it points to 2, and 2 points to, let's say, 3, and 1 also points to 3. So if you look at this graph does not contain a cycle, and but if you just change the direction of edges, maybe 2 points to 3 and 3 points to 1, so this graph is not a DAG, but this graph is a DAG. Okay, so this is what a directed acyclic graph looks like and why it is used. So it says basically we can say let's say 2 is a task and 2 is dependent upon 1. Let's say 3 is a task, 3 is dependent upon 1, and 3 is also dependent upon 2. So what we want from topological sorting is we want such an ordering, okay, for every directed edge that is there from u comma v, vertex u comes before v in the ordering. Okay, so if we do some ordering of this graph, so 1 should come before 2 and 2 should come also before 3, because 3 is dependent upon both 1 and 2. Okay, so it is not possible if the graph is not a DAG. Okay, so in this case the graph contains the cycle, we cannot figure out the dependencies. Okay, so what is the meaning of a dependency? Let's say, let's take a very real life example. For example, you have multiple tasks. Let's say task 1 is you have to, let's say, wear shoes. Okay, and let's say task 2 is you want to wear socks, okay, and maybe task 3 is um you want to wear a pant also, okay, you have to wear a jean also, okay. Now what may happen is, if I want you to come up with an order, okay, so clearly we know we cannot wear shoes before wearing jeans and before wearing socks, okay. So in order to wear shoes, we should wear socks and we should also wear jeans. So shoes has a dependency on two items. Shoes is dependent upon jeans and shoes is also dependent upon socks. So between jeans and socks, you may have a dependency, you may not have a dependency, okay. Maybe you can first wear jeans, then you wear socks, and then you wear shoes, okay. So one possible ordering could be jeans followed by socks followed by shoes. But sometimes maybe you're not wearing jeans, you start with socks, then you wear jeans, and maybe then you wear shoes. So in this case, both of these orders are correct, okay, both of these orders are correct. And you can see this is what the topological sorting of this would look like. Now you may ask, why do we need such kind of a sorting? So now you may ask, why do we need such kind of a sorting? So it has lot of applications. So it has applications in job scheduling. Given a complex dependency tree, you want to figure out which jobs should be executed first or in what order. Similarly in instruction scheduling, and there are some more applications which we are not going into detail. So one very common application I have seen is on the servers when you have to compile your code, okay. So in during compilation there are multiple dependencies. Maybe you want to build a file C that is dependent upon B is dependent upon, let's say, D, and maybe B is also dependent upon A, and D is also dependent upon A. So if you have this kind of a structure, you need to resolve the dependencies, okay. So first you will compile A, then you will compile D, then you will compile B, and finally you will get the output C. So this is the topological sorted order for this kind of a graph, okay. So what we will do, we'll go through one example and we will discuss the algorithm how we can do topological sorting, okay. So this we will see in the next lecture. Hi everyone, so welcome to the topological sorting algorithm. Now what we want to do is, we are given this kind of a graph. We want an algorithm that gives us the correct order in which the tasks should be executed so that we are able to execute all the tasks. Firstly, you need to check whether it is a directed acyclic graph. So yes, this is a directed acyclic graph. It has directed edges and it does not contain a cycle. Now what we can do is, if you look carefully at these graphs, so in order to, let's say, execute a node 5, we must complete task 3 and we must complete task 4 as well. But in order to complete 4, we must complete task 1, okay. So there are certain dependencies for every tasks. But if you look carefully, you will realize that there are two tasks which don't have any dependencies, okay. So there are task 1 and task 0. They are not dependent upon any other task. So what you can do is, you can actually with every node you can store what is the number of dependencies for this task. So for this it is 0, for this it is 0, and for 4 it is basically equal to in degree, the number of edges that are coming in that particular node. So we are going to calculate in degree for every node. So that would be the step 1. So in degree for 1 and 0 is 0, for 4 it is 1, for 2 it is 2 because we have 2 incoming edges, and for 3 it is 1, and for 5 it is again 2. We have 2 incoming edges. Okay, so in the next step what we are going to do, we are going to put all these nodes. So what we are going is, we are going to use a BFS for this particular algorithm. We can also do it using DFS, that we may do later on. Okay, but for now let us first focus on BFS. So what we do in BFS, we start with a queue and we initialize some nodes in the queue. Okay, so here we can put both 1 and 0 inside the queue. So 1 goes here and 0 goes here. Now what do? You pop out one node. So you extract 1, you say okay, I have completed task 1. So as soon as you complete task 1, what will happen, this dependency will get removed and this will get removed. Okay, so that means the in degree of 4 will be now 0, and in degree of 2 will be reduced by a value of 1. So this in degree is now 1. So those nodes which have a 0 in degree, we will put them inside the queue. So 4 goes inside the queue and 1 is removed. Okay, so we print we have completed task 1. So here I am going to write the output. What we do in the next step, so we pop out 0, and 0, if you do complete task 0, the dependency of 2 will reduce, so it would be now 1 minus 1, that is equal to 0. It has now an in degree of 0, so this will get added in the queue, and we are done with the task 0. We remove it. Next is 4. Okay, so let us complete task 4, and 4 now has edges to only 5, so we will reduce the in degree of 5 to 1, and we will not put 5 inside the queue because it is not yet ready for processing. It has certain more dependencies. So that's it. 4 has only one edge, so we don't do anything. 4 gets removed and 4 is printed. Then we can see the next node in the queue is 2. Now 2 doesn't have any dependencies. It was dependent upon 1 and 0. Both are done. So we remove 2 from the queue and we print it. And by doing so, we will also able to reduce the dependency of 3. That is now reduced to 0. So 3 is added to the queue. And now we pop out 3. 3 is gone. 3 is printed. And as we remove 3, we can see dependency of 5 is reduced by a value of 1, so it becomes 0. So 5 is added into the queue, and finally you will remove 5. 5 doesn't have any further edges, so we will not do anything else, and now the queue will become empty. Queue is becoming empty now. Okay, so once the queue is empty, that means we have printed all the nodes, and this is one way to order the tasks. Okay, or order the nodes. So this is one correct output. So there can be multiple outputs. possible. In some other output you may have 0 in the beginning, then followed by 1, then maybe followed by 4 2 3 5. Okay, so topological ordering can have multiple outputs. You have to print one such output. So I hope this algorithm is very intuitive and it is clear to you, and in the next lecture we will write the code. Hello everyone. So let us discuss the topological sorting code using the BFS based method that we have just discussed. So let's begin. So what we are going to do, for in the first step we are going to calculate the in degree for all the nodes. So what I can do, I can here include vector, and I can say we are given this graph which is stored in the form of an adjacency list. So I can say vector of integers, I call it as in degree, and it has v nodes and it is initialized with 0. Okay, so every node has a in degree 0 in the beginning. Then what we can do, we can iterate over all the edges, iterate over all the edges to find the right in degree. Okay, so for int I equals to 0, I less than v, I plus plus. So I'm iterating over the adjacency list for, I can say, auto neighbor. Let's say there is an edge from node x to y. Okay, let's say there is an uh, in the adjacency list of, there is let's say we are storing x has edge to y1, y2, y3. Okay, for example, like 1 has an edge to 2 and 3. So we are iterating over this. Well, like node x to y. Okay, let's say there is an, so I'm iterating over the adjacency list for, I can say, auto neighbor. Let's say there is an edge from node x to y. Okay, let's say there is an uh, in the adjacency list of, there is let's say um, we are storing x has edge to y1, y2, y3. Okay, for example, like 1 has an edge to 2 and 3. So we are iterating over these values. So we can say for every y, that is there in list of I. Okay, or for every neighbor that is the neighbor of the node I, what we can say, we can say in degree of neighbor plus plus. Okay, so basically for example, we are iterating over this edge 1 to 2, we can say in degree of 2 is 0. Now it is incremented to 1. Then we iterate over this edge 0 to 2, we say in degree of 2 should be changed by a vector of 1. So this in degree is 2. So we iterate over all the edges from, let's say, u to v. So we increment in degree of v by a factor of 1 if there is an edge from u to v. Okay, so this is what we do. So this is how we initialize the in degree. Now what we can do, we can do the BFS kind of a logic. So we need to create a queue, and we need to initialize the queue with nodes which have 0 in degree. Okay, initialize the queue with nodes having 0 in degree. So let's iterate over all the nodes for I equals to 0, I less than v, I plus plus. If in degree of I is 0, I can say q dot push I. That's done. And after that, what we can do, we can start popping nodes. Okay, so I can say while this queue is not empty, do one thing, pop out the node which is there at the front of the queue, because it must have a 0 in degree. Okay, so all the nodes in the queue must have a 0 in degree. That means they don't have any dependency and they can be removed and processed. So let's print that node. Let's remove that node using the pop function. And what we need to do, we need to iterate over the neighbors of this node, and we need to reduce their in degree by a factor 1. So for auto neighbor that is there in the adjacency list of this node, we can check in degree of that neighbor is reduced by a factor of 1. And we can also check if at any point this neighbor has a in degree 0, that means it is now ready for processing and we can push it into the queue. That's it, queue.push neighbor. Okay, so this is pretty simple. And now what we can call g dot topological sort. Okay, so let's try to run our code, and we're getting this output 0 1 4 2 3 5. So firstly we complete the task 0, then we complete 1, which is fine, then we complete 2, then we complete 3, then we complete 4 and 3 and then 5. So yes, this looks like a perfect output. That means our code is working as expected. So what we are doing here is, suppose we have a node that is there inside Q, so it must have a 0 in degree, and let's say from this node we are having connections to some other nodes. Let's say this has a in degree 2, this has a in degree 1, this has a in degree 1. So what we do, if we remove this node, that means we have done this task, these edges can be removed. So what we do, we iterate over the neighbors of this node and we reduce their in degree by 1. So this in degree becomes 1, this in degree becomes 0, this in degree becomes 0. That means these nodes don't have any dependencies, so they are added to queue for further processing. Okay, so this is what I have done here, added to queue for processing. That's it. And this is how we have done topological sorting on a directed acyclic graph. So I hope you like this